Yeah.
Okay, so what I'm going to do today is find the possible eigenstates of the spin operators. The reason for that stems from the Casimir operators of the Lorentz group, of the Poincare group, which we use to classify particles. I won't talk about that yet. For right now, let's just look at the fundamental commutators for the rotation group. And we've shown that these take the form Ji, Jj is I believe, yeah, I, H bar, epsilon I, J, K, J, K. And what we use to classify particles is J squared, the sum of squares of the three J's. And so in addition to mass, which again I'll talk about later, there's a quantum number J such that J squared acting on this gives J plus 1 H bar squared times the state. So basically, because this is a Casimir operator, we know we can diagonalize it. We know we can. This operator commutes with all of the J's, and so we're going to choose.
Yeah. What is the definitions of the J's again? I forgot. Ji, Ja, Jj, Jk is understood.
These are infinitesimal generators of rotations, three-dimensional rotations.
So how is the J different from the I, J, and K?
Ji, there are three of these. Okay, this is J1, J2, J3.
Oh, I see.
So I or J or K
goes 1 to 3.
From 1 to 3, and these, if we exponentiate, let's see, well, with real parameters, these things of this form will be elements of the rotation group, either SO3 or SU2, depending on the representation. There could be other representations. These are the ones we've studied. Now, we know that the Pauli matrices satisfy something like this. Sigma I, sigma j is 2I epsilon I, j, k, sigma k. So if we divide by 2, let's see. So let's let tau be 1/2 sigma I. Then if I multiply both sides of this by 1/4, then this side becomes the commutator of 2 taus, and this side becomes, right, we're left with 1/2, but that becomes a tau, so we just have I, epsilon I, j, k, tau k. So just 1/2 times the Pauli matrices satisfies this. So we know several, and we've also found some real 3x3 matrices J that satisfy these commutation relations, up to some multiple. We probably didn't have the IH bar there then, but we're talking about quantum spin here, so we put it in.
Okay.
Now,
you are trying to diagonalize.
Yeah. So the background of this is that there are two operators, P squared and J squared, that are the Casimir operators of the Poincare group. Those two operators commute with all of the generators of the Poincare group. And because of that, we can use those to invariantly classify states. So acting with the Poincare group won't change the values of the eigenvalues, won't change the eigenvalues of those two operators, one of which is J squared, and we're going to label states by J where the eigenvalues of J squared are given by J plus 1, H bar squared. Okay, so we don't know a priori that that's the right way to label the eigenstates. So what we want to do to actually find all of the states is to first find a set of maximally commuting observables. Well, we know that each of the three j's commutes with j squared. It's a Casimir operator, so they commute. But none of them commutes with the others. So we can diagonalize at most one of these, and we usually choose J3. So we know we can simultaneously diagonalize both J squared and J3. Now, the eigenvalues are now what we want to determine. So basically what I'm going to be doing here is determining those eigenvalues. Let's not make any assumptions about the eigenvalues. It's going to turn out to be this, but let's just say for now that J squared acting on a state is in, let me see how I label this in my notes. And these are all operators. Everything should have a hat on it here. Everything inside is a quantum operator. Okay, so the result of J squared is going to be alpha h bar squared times the state. So since these commute, we can simultaneously diagonalize them. So we'll call alpha and beta the eigenvalues of these. So beta, and I'll put an h bar here. Just that makes things dimensionally correct. Beta h bar, yeah, good. Now, from the remaining operators, we also have operators J1 and J2. And from these, I'm going to construct two new operators, different linear combinations called J plus and J minus. J1 plus or minus IJ2. And we need to find the properties of those. Are you familiar with these? The raising and lowering operators?
Lowering, yeah, I remember
Okay.
that. Yeah.
All right. So we would like to know how they interact with each other and with J3. So of course, J plus commutes with J plus and with J minus. If I compute the commutator of J plus with J minus, that's J1 plus I J2, J1 minus I J2, and that's minus I J1 with J2 plus I J2 with J1. And this is minus that, so we're going to get two of those. So we get 2I, and now let me call it minus 2I. J1 with J2, coming back to our fundamental commutator, is IH bar epsilon 1, 2, 3, J3. Well, epsilon 1, 2, 3 is 1. So we get IH bar J3. IH bar J3. And so the I times minus I is 1, and we get twice H bar J3. Now, we also need the commutation relation of each of these with J3. So J plus or minus with J3 is going to be J1 plus or minus I J2 with J3. And J1 with J3 is I H bar epsilon 1, 3. It's got to be 2 J2. And plus or minus I times J2 with J3 is I H bar epsilon 2, 3, 1 J1. And now, epsilon 2, 3, 1 is a cyclic permutation of 1, 2, 3. So that's plus 1. And 1, 3, 2 is a single interchange, so this is minus 1. So what we get is going to be, here we have minus or plus h bar j1, and here we have minus I h bar j2. So let's see, if we pull out minus or plus h bar, then I can write this as j1 plus or minus I j2. And that's minus or plus h bar j plus or minus. So it's, or that I wrote that in the wrong order. Yeah. So no, this is just minus j3 with j plus or minus, and that makes it easier to remember.
J3 plus or minus.
Yeah, let's write j3 with j plus or minus.
Plus or minus.
Plus or minus h bar j plus or minus. There we go. That's right. And then the one we got over here, j plus with j minus, is twice h bar j3. So this is simply a different way of writing the same Lie algebra. Right, we've taken some linear combinations. It's just a different basis. And then recalling that j squared commutes with everything, we know that j squared will commute with both j plus and j minus. Now, let's see what we can do. What I want to study is the action of j plus on one of these eigenstates. So look at j plus on alpha beta. If I act with j squared on that state, j plus alpha beta, these commute. So the j squared just comes in and gives its usual eigenvalue. So we're just going to get alpha h bar squared
J
plus on alpha beta. We just move the j squared past and let it act. So j plus does not alter the eigenvalue, the alpha eigenvalue. If we look at j3 acting on j plus alpha beta, now we can write that as j plus acting times j3 using the commutator. The commutator of j3 with j plus is plus h bar j plus. So j3 j plus is equal to j plus j3 plus the commutator. And that then acts on the alpha beta state. But now I can let the j3 act and pull out the beta. So, and that gives, j3 on this eigenstate gives beta h bar. So what I get is beta h bar plus h bar with j plus acting on alpha beta. And we can write that as beta plus 1 h bar j plus alpha beta. So the effect of j plus acting on a given eigenstate is to give an eigenstate with one higher value of beta. That is, it must be the case that this state, j plus on alpha beta, is proportional, some proportionality constant to having the eigenvalues alpha and beta plus 1. Then if we do it with j minus, what happens? Well, I give this as an exercise, but I think you can see what happens. The only difference, if I had a j minus here, right, this still commutes. This is still the same. But acting with j3, if I have a j minus here, right, if I had a minus here, it would be plus or minus everywhere. And so then the eigenvalue of j3 would be beta h, but then I would have a minus here. And so I would get beta plus or minus 1. And so j plus or minus is going to raise or lower the eigenvalue beta by exactly 1. Clear?
Yep.
Okay, so let's move back down to this end. And now I want to look at products of j plus and j minus. So if I look at j plus times j minus, that's j1 plus I j2 times j1 minus I j2. And if we multiply that out, that's j1 squared. And then we have I, let's write it as minus I times the commutator of j1 with j2. And that's both the cross terms, this one minus that one. And then finally we get plus j2 squared. And now, since j squared is just the sum of squares of all three, I can write j1 squared plus j2 squared as the total j squared minus j3 squared. And then I know that the commutator of j1 with j2 is I epsilon 1, 2, 3, j3. So finally, I can write j plus j minus as j squared minus j3 squared plus epsilon 1, 2, 3 is 1 plus j3. Just check that. I lost the h bar. There's an h bar here. H bar j3. Yeah, that makes it easier squared. That needs the extra h bar. Now, if we do this in the opposite order, j minus j plus, the only thing that changes, okay, we would have a minus here and a plus there, so this cross term would have the opposite sign. That's the commutator term, so it's only going to change the sign of that third term to minus h bar j3. So we've got j plus j minus is j squared minus j3 squared plus h bar j3, and j minus j plus, if we take them in the opposite order, is the same thing but with the minus sign. Okay, now.
So is that when they like act successively on?
Yes.
Okay.
Yeah. So we know what these are going to do, right? We know how these act on these eigenstates, on these eigenvalues. So let's take a look at that, because we now have two different ways of expressing the action of those compound operators on eigenstates.
Yeah.
So, Davis, we've seen that the generators for the rotation group in 3 dimensions satisfy I epsilon ijk. We can rescale this any way we like. Let's do it so there's an I h bar there. Then the units are right, and then we just exponentiate I times the j's. But they satisfy this commutation relation. What we're doing is finding essentially all states that for which we have operators that satisfy this. Basically, we're going to find all representations for the j's. We found 2, right? We found complex 2 by 2 matrices, basically the Pauli matrices satisfy this. And we found real 3 by 3 matrices, antisymmetric, that satisfy this.
So is that the SU3 and SO3?
Yes,
SU2 and SO2.
SU2 and SO3.
Okay.
All right. Those are two representations of the rotation group. We're going to find them all.
Oh.
Right. So it hinges on this. The other thing we're using is that if we sum the squares, J1 squared plus J2 squared plus J3 squared. I'm omitting all the hats on everything. There's a hat on every side, right?
Yeah.
Okay. This is a Casimir of the Poincare group and of the rotation group. This squared operator commutes with everything. You know, I didn't show that. Let me just quickly show that. So if I have J squared with it doesn't matter which one I pick, J1, J2, J3. Let's just do J high, and any of the three. Then this is a sum on J. So let's write J squared this way. And when I have a product of two operators, I can pull the left one out this way and look at the commutator like that. And then I can pull the right one out
the other way.
Side
Yeah.
and write JJ. Now these happen to be the same, right? But still, I can use the trick.
Mm-hmm.
And now JI with JJ is IH bar epsilon JIK, and then we have this JJ, and this gives us a JK. And here we have IH bar. Let's see, it's not quite the same. The JJ is on the other side.
Mm-hmm. But the IH bar will be there.
Yeah, we have the IH bar. We have epsilon JIK JK now, and then the final JJ.
Yeah.
And so this is IH bar epsilon JIK, but then times the symmetrized product JK JJ. This is symmetric, this is anti-symmetric, so we get
0. Yeah.
Okay, and yeah, we could commute those and subtract.
Yeah, sure.
But anyway, symmetric versus anti-symmetric. So J squared commutes with all three of these.
Mm-hmm.
So then what we did is to note that since J squared commutes with all three, it commutes with any one. This is 0. Now, this gives us a maximal set of commuting operators, right? We can't add another one, J1 or J2, because they don't commute with J3. So this is a maximal set. So we define eigenstates, alpha h bar squared. The h bar squared just keeps the units right. So we define simultaneous eigenstates of these two commuting operators. And so we assign alpha and beta as the eigenvalues. And what we want to do now is find all values of alpha and beta. So to do that, we defined two operators, J plus and J minus, defined to be J1 plus or minus I, J2. We found the commutation relations between J plus and minus and each other. And any of these that, I'm not showing you now, do as an exercise.
Yeah.
But you get J3. And then J3 with J plus or minus gives plus or minus to J plus or minus. And we use that to see what J plus or minus do to a state. So if I look at a new state, either J plus or minus acting on one of our simultaneous eigenstates, then I know what J squared does with that because J squared commutes with those. So it just comes through and pulls out its usual eigenvalue. J3 does not commute with it. J3, using the commutator, I can move the J3 past J plus or minus,
Oh,
but I pick up the commutation relation.
Right.
And now I can pull out the J plus or minus, and there's my state again. But the coefficient, the J3 pulls out a beta H bar, and I had this H bar from the commutation relation, which means that this operator has raised or lowered that beta by 1 unit exactly. So if the state alpha beta has an eigenvalue beta H bar for J3, then acting with J plus or minus has eigenvalue beta plus or minus 1. Let's label this coefficient. What that means is that this combined state is still an eigenstate of both J squared and J3. But the J3 eigenvalue has changed to beta plus or minus 1. Okay? So the J plus or minus let us move from one eigenstate to another in unit steps. Without changing alpha, it has changed beta.
I see.
Okay, so let's see, we were back over here.
It's not quite acting like the ordinary quantum mechanics lateral operators. Like A dagger?
The A and A dagger.
Yeah. Not quite.
Not quite.
Yeah.
Yeah, they don't change alpha, but they're acting that way on the betas.
Right.
They're raising and lowering J3, the Z component of spin. They're not changing the total spin.
I see. Got it.
Okay, so let me erase some things.
Again, the J's are the generators for the SU2 layout.
Not quite.
Rotation.
They are generators for the rotation group,
Okay.
but we haven't specified any representation.
Oh, I see. Oh.
They could be the SU2 generators, they could be the SU3 generators, they could be some other generators.
I see.
What we're going to find is all possible generators. Right? Because this state of eigenkets, the alpha beta kets, that's going to be a complete orthonormal basis. So
Is this how we find a faithful representation?
Well, we have a couple of faithful representations, but
Like finding all the generators.
This is how we find all representations.
Oh, I see.
These are all faithful representations.
Okay.
So, I think that's fair to say. Notice that SU2 is a two-dimensional representation. SO3 is a three-dimensional representation. We're going to find a representation of every dimension.
Oh.
Right? So we'll see that there are vector spaces of every dimension on which these J's act in a sensible way. So these alpha and beta kets, these eigenkets of J squared and J3, for different values of alpha and beta, will give us different representations for the J's. So, okay, so the last thing...
The three are two-dimensional representations. Will they correspond back to SO3 and SU2?
Yeah.
Okay.
Yeah. Okay, so we worked out these products. J plus with J minus with J plus. Just by squaring them out, then noticing that we had a J1 squared plus J2 squared, which could be written as the total J squared minus J3 squared. And now we know how to act with both of these. And then the commutator of J1 with J2, which is a J3, which is nice because, okay, we now know one way that J plus and J minus act on the alpha beta states. We also know how these operators all act on those states. And this can give us some new information about these states. We're going to develop some inequalities now. So notice that J, which way do I want to do this? J plus dagger. Since the J's are Hermitian, these are observables, right? So J plus dagger just changes the I and you get J minus. What that means is if I have any state and I act on it with J plus, then the state dual to that is
Right.
it's a bra with the dagger.
It's J minus.
So this state is dual to that one. So if I take the inner product of those, alpha, beta, J minus, J plus, alpha, beta, that's the norm of this state.
Right.
That's got to be positive definite.
Yeah.
Okay, so the norm of any, it could be 0 if it happens to be the 0 state, which, let's see, well, in some situations that's possible. I don't think that happens here, but that'll happen sometime. Then we can do it the other way. We can take minus here, and then the adjoint is plus. So we can take the norm of J minus on alpha beta, which could be 0.
Yeah.
We'll see. And then we get this. And that's the norm of a state, so that has to be non-negative. But now we know how to evaluate these things. And actually in 2 different ways. So let's see. Yeah, well, one way is going to be sufficient. So what we have is this first one is greater than or equal to 0. That's alpha, beta. Okay, now J plus, J minus. J minus, J plus, we've shown to be this operator right here. J squared minus J3 squared minus H bar J3. So we'll just substitute that, and then we have alpha beta. And we know how to evaluate these. So alpha beta here, right? These are eigenstates, so we're just going to pull out some number here.
Yep.
J squared gives us alpha H bar squared. J3 squared gives us beta squared H bar squared. And then J3 gives us beta and another H bar, so H bar squared.
But
J3 or J3 squared.
oh, got it.
Okay, and then we're back to alpha, beta, and so the inner product of alpha, beta is some positive number. That's definitely non-negative, and so this means that we have to have alpha minus beta squared minus beta has to be non-negative. Canceling the H bar, canceling the norm of the alpha beta state. And now we do the same thing for this. Let's see, this was with the minus here. That's
J minus J plus. That was the first one. J minus J plus.
J minus J plus. That was the first one. So the second one is going to have a plus H bar here.
Yeah.
Okay.
So it's just going to change the plus.
It means it's going to be a plus beta. So we're going to find alpha minus beta squared
Plus beta
has to be greater than or equal to 0 as well.
Right.
Okay. Okay. So now, if we bring things to the other side, alpha has to be greater than or equal to beta squared plus beta, and alpha has to be greater than or equal to beta squared minus beta.
Yeah.
And let me just check myself here. Yeah, that's right.
Yep.
Okay. So now we're going to generate a contradiction with this. Well, not quite a contradiction, but
What is the structure constant for SU2?
Levi-Civita.
Yeah.
That's
So
JK.
yeah. Right.
Yeah.
So that's why.
So the poly matrices satisfy this.
Right.
Yeah. So do those real anti-symmetric 3x3s.
Oh, okay.
Right.
So it's not quite
There's not a unique thing that
Okay.
satisfies that.
Okay.
Okay, so what we do here is, it's a lot like the harmonic oscillator. What we're going to do is act with J minus a bunch of times. So suppose we look at the effect of J3 on J minus, but let's let J minus act K times. All right, well, we know what that does because up to some normalization, right? So there's some overall constant lambda, but this is going to give us J3 acting on alpha and beta minus K. It lowers beta 1 each time. We add K times, it lowers it to this. J3 acting on that is going to give beta minus K times H bar. Now, that's a bit of a problem for these inequalities. That means that these inequalities can't go on forever.
Where's that?
Right, well, I'll show you. We have to have alpha squared greater than or equal to, and let me see which one I use here, this sum, beta squared plus beta.
Yep.
And beta squared plus beta, okay, as we lower, that's going to be beta minus K squared plus beta minus K, which is our beta squared minus 2 beta K plus K squared plus beta minus K, which is, all right, let's pull the K squared out here. Then we have, minus 2 beta plus 1 K plus beta squared plus beta. Okay, now, as K increases, this K squared term dominates.
Yeah.
We can make this side as large as we like.
Oh, yeah, sure.
But eventually, it's going to run into alpha. And so we can't go any further. So as soon as this side becomes larger than alpha, it's not possible to generate a new state. Right? We generate a new state, we get something that violates this inequality. That can't be the case. So the only alternative is that, let's see, all right, suppose, let's just be rigorous about this. Suppose J3 for J minus to the nth power on alpha beta gives us lambda, all right, that's going to be beta minus n h bar alpha beta. And further suppose that n squared minus 2 beta plus 1 n plus beta squared plus beta. All right, subtract that from alpha squared. Suppose that is between 0 and 1. Suppose it's less than 1 and still positive. Let's see. Well, less than or equal to 1 would be fine. Then if I act with one more J minus acting on J minus to the n alpha beta, it can't be beta minus n minus 1.
Right.
Because that would violate the inequality. The only option is that we get 0. It has to annihilate that state. It's not allowed to produce any new state. All right, so
it annihilates the whole spin.
it just kills the state. Yeah. Yeah. Well, it's like the simple
A
harmonic oscillator is like A acting on the vacuum state.
The ground
Yeah.
state.
A kills the vacuum state.
Yeah.
Okay, so what this means is that there's a minimum value for beta. For any given alpha, for any fixed alpha, there exists beta min. Right? It's basically this beta minus capital N, such that J minus on alpha beta min is 0. So we've established the existence of the lowest state.
And this is eventually going to describe a field?
No, that's not where we're headed here.
I'm trying to...
We're trying to classify possible fields. Okay, yeah, you weren't here for the beginning discussion, and I was going to wait until everybody was here.
Oh, okay, yeah.
But no, I'll tell you, I'll hear it again. Won't hurt to hear it again. There are certain operators called Casimir operators for any Lie algebra, right? They're products of the generators, combinations of the generators that commute with all of the generators. For the Poincare group, there are 2 of these. One is p squared, the translation generator
Projection.
squared. No, not
yeah, okay.
p momentum.
Yeah, okay.
P squared, and the eigenvalues of that are mass squared. The other, you can write it with the m's and the p's and a Levi-Civita tensor, but it amounts to, when you choose the basis right, it amounts to the j's. It amounts to j squared, right? Now, that means that j squared commutes with all the Poincare generators, and so we can label all physical states that have Poincare symmetry by their mass and their spin. Right? So all of our physical states are going to be states of definite mass and definite spin, because those Casimirs commute with all of our Poincare transformations.
I see.
Right? It's a physically meaningful way to do it. You boost, you translate your frame, you still have those labels for your states. Everybody can agree on those labels. So mass can be anything so far as we're concerned here.
Right.
It actually, we'll get to the Higgs and things and see what mass might be. But for spin, we would like to know all possible representations of the rotation group, so we can know all possible values of j squared. And that's what we're finding.
Oh.
So this is a bit of a side, a bit of a digression to explore all possible states of angular momentum, because they will label our physical states, our physical fields. And what we're going to find is that we can label our physical states by the mass and by the eigenstates of j squared, which will turn out to be any integer or half integer. Right? So that's what we're proving now. This is a calculation that's often done in quantum mechanics classes, right? And it's in my quantum notes, but I've appended it here because it's relevant for the classification of our particle states. Okay, so we've established that there's a minimum value for beta. And now if we, let's see, okay. All right, now beta min is actually less than 0. If you look at beta equals 0, this is satisfied. So beta equals 0 is fine. Let's see, -1. We've got this will be +1, -1, so that's satisfied. If it's -1, that's that could be 2. Well, that's satisfied for some alpha.
Right.
So we expect beta min to be 0. I'm sorry. We expect beta min to be less than 0. It could be equal to 0, but what that means is that we need to have where's the inequality here? Beta squared plus.
Beta squared plus beta?
Well, let's look at the -1. Beta min. If
Squared.
we look at, the beta min minus beta min.
Yeah.
Has to be this has to be less than alpha squared, and less than or equal to alpha squared.
Where did you get the square?
I'm looking at this one. Beta squared. So put beta min in here.
Yeah.
And this has to be set.
Oh, yeah, because beta mean is related to alpha.
Just alpha.
Okay. Yeah, that was.
Now let's see if we work this the other direction. Let's do the same with J plus to the K on alpha beta.
Yeah.
The same thing is going to happen. The only difference is we have beta plus K here and here. So we have plus signs everywhere. We still end up with a leading K squared, which is eventually going to be bigger than alpha. So there's also a beta max. There exists beta max.
For the same argument.
Same reason, same argument. Yeah, and now beta max will be positive, and we need to have beta max squared plus beta max less than alpha. So we have these two inequalities. These are satisfied by some integers. But now, let me see. Okay, I'm going to need to remind myself of this argument. But notice if beta minimum is minus some integer, then we're going to have m squared plus m less than alpha. If beta max is plus m, then it's going to give the same thing. M squared plus m less than or equal to alpha. So that's just an aside. That doesn't mean that's true, but we're going to find something like that. So, but let's go work through this argument carefully. Yeah, I've called the eigenvalue alpha squared, but here I've called it alpha. I'll keep calling it alpha. Okay. We know that J plus acting on alpha beta max is equal to 0. Yeah. So now, and similarly, J minus alpha beta min gives 0. And now I think what we want to do is step between these. Yeah. So
get some type of product.
Let's act with J minus on the beta max state and J plus on the beta min state.
Okay.
All right, so we want to raise those up. So yeah, what's going to happen? All right, this is going to be something with an alpha beta min plus 1, and this is going to be some constant, but it's proportional to beta max minus 1. So now I can act on this with J plus and this with J minus. J plus here and J minus there. And this will raise it back up. So this will be some
New constant.
different lambda, but we're going to have alpha beta max again.
Yeah.
And here we'll have some lambda double prime, let's call it, with alpha and beta min.
Yeah.
Okay, so now I think we can find those constants because, let's see which one we want to do here. Yeah, so let's number these and just look at them. So number 1, we can rewrite J plus J minus, I just erased, but J plus J minus is J squared minus J3 squared plus H bar J3. And that acting on alpha beta max is going to be, that's lambda prime alpha beta max.
Right.
But we know what this is, right? Because J squared is going to pull out an alpha H bar squared.
Yeah.
And J3 is going to pull out 2 copies of beta max times H bar. And then we're going to get H bar, then we get another H bar times beta max.
Must
So
be lambda prime.
That's the lambda prime.
Yep.
Oh, and I've done it backwards. Rats. I should have applied these to these so I'd have zeros. Sorry.
Oh, okay, okay.
Oh, all right. So yeah, let's revise this. J plus on this state is 0. So J minus J plus on that state is 0. So J minus J plus on alpha beta max is equal to this, is equal to 0. That's a better identity. Because that gives us a number that's equal to 0. What is it? It's alpha H bar squared minus beta squared H bar squared minus H bar squared times the single beta max.
Yeah, these are all beta maxes.
And that has to vanish.
Right.
And the H bar squareds all go out.
Yeah.
So what we have is alpha is equal to beta max squared plus beta max. Ah, good. That's better. And now for the other one, now let's do it for this one. So we also know that J plus acting on J minus acting on beta min has to be 0.
Yeah.
And we have the same argument here. Okay, the only difference here is we're going to have a plus here.
Yeah, so it will be beta max squared minus beta max.
Right. So what we're going to get is alpha equal to beta min
Sorry, yeah.
squared
Min.
minus
In this case.
beta min.
Yeah. Okay.
Okay, good. Better and better. Okay, and this agrees with my notes. Good. Okay. Now, we also know that we can step from one of these to the other. Because if we start with beta min and act with J plus, we're eventually going to get up to beta max and then get 0. So beta min plus some integer k has to be beta max.
Right.
And now from these three things, I think we can solve for beta min and beta max. Let's equate the two. Yeah, let's come up with that.
Let's equate what to?
So we have two expressions for alpha here.
Okay.
So we see that beta max squared plus beta max has
So
to
beta
equal
is 0.
Beta min squared minus beta min, right?
Oh, no. Okay.
Each of these
Yeah.
equals alpha.
Yeah. Yep.
Okay, but now beta max is beta min plus k
Yeah.
plus
Beta
min
max
plus k has to be
Okay.
beta min
squared.
squared minus beta min.
Yeah.
Okay, so now we can just solve for beta min. We get
So the
beta
squared will cancel that one.
plus 2k beta
Beta.
min plus k
K
squared.
squared plus beta min plus k.
So the beta min square vanish.
Okay, so those go out. Let's bring all the beta min stuff over here. So let's see, we have a 2k
Plus 2.
plus 2. And
K.
then on this side,
Minus k plus k squared.
oh, it's negative. Okay,
Yeah, that's
good.
what I mean. So
Yeah, so so beta min is minus, then we can write this as k times k plus 1.
Yep.
Divided by twice k plus 1 is minus k over 2. And immediately beta max equals beta min plus k equals plus
k over 2.
And so the possible values for beta max and beta min are any integer multiple of a half, any non-negative integer times a half. So, we actually basically knew that, right?
Yeah.
Now, we can also find alpha, right? Alpha, we can use either of these. Let's say k over 2 squared times plus k over 2. And then that's, let's see, let's define this to be a number j. So,
No, I think we're getting alpha from there. Beta min squared minus beta min. Is that not just easier?
neither one's very hard.
Well.
This is j plus 1.
Okay.
We can check the other. It also has to be minus k over 2 squared minus k over 2 gives the same thing. That's going to be k over 2 squared. That becomes plus k over 2. And we've called that j. That's j plus 1. So either way, we had to get the same thing. Now we do.
Beautiful.
Okay, so we're defining these to be we're defining that k over 2 to be j. So j can be 0, 1 half, 1, 3 halves, and so on. Any half integer. And now I think we're there because we can write all of the eigenvalues. So let's let beta now. All right. Let's define it to be m. So then that means that our states alpha, beta, we're going to write as j and m, where j plus 1 is what we found for alpha. So this is alpha, this is beta now. So j squared on j plus 1 m is going to give j plus 1 times h bar squared times j plus 1 m. And j3 acting on this is going to give m h bar times the same thing, where m runs from minus j plus 1 up through 0
Plus j.
Might not hit 0. If this is a half integer, you're not going to hit 0. But you'll get down to j minus 1 up to j. So that's in general 2j plus 1 values. Is that right every time? Yeah.
If it's 2,
Right.
it's gonna be 3.
Yeah, so certainly for any integer, you hit 0, so you get positive integers,
Right.
the negative integers, and
And
zeros.
zeros.
Now, if it's a half integer, you're going to miss 0, but you're starting in a half, so you go minus a half straight to plus a half. 2 times a half plus 1 is 2. Well, there are 2 of these values. So there are always 2j plus 1 values for m. So now, rather than writing j plus 1 all the time, I'll introduce a shorthand. Instead of writing this, I'm going to write it as just j and m. If we know j, we know j plus 1. So now, j squared on a jm state is j plus 1 h bar squared times jm. J3 on a jm state is m
You mean the
h bar.
the old j.
This j, this j.
All right. Okay.
I'm just avoiding writing j plus 1 all the time inside my kits.
Yeah.
Because if I know j,
Right.
If I know j, I know that's the eigenvalue.
Right.
Okay. So these are the possible eigenvalues of j squared and j3. So now, in what sense is this all of the representations of
Right.
of the rotation group?
That's the punchline.
So we have one representation of every dimension.
And it's quite an audacious claim when you think about it.
Oh yeah, yeah.
You know.
Somebody clever figured this out. Right. So this is all possible representations
In any dimension.
of the rotation group. In 3D,
Okay.
the three-dimensional rotation group. Okay, so let's look at j equals 0. All right, at 0, m has got to be 0. There's one state. That's a one-dimensional space. one-dimensional vector space. This is the basis. We can take, multiples of that,
Yeah, sure.
right? So it's a one-dimensional vector space.
Mm-hmm.
And there's a representation of the J's that act on that. Well, what is the representation? Well, we can find matrix elements for J squared and J3. All right, so just sandwich them between all possible states. Right, so J squared, 0, 0, well, this is boring because it's just 0.
Yep.
And J3 is going to give us 0. So both of the representation for both of these is 0. It's a 1-by-1 matrix, acts on a one-dimensional vector space. These are generators, so if I exponentiate some WJ3, I just get the identity.
Yeah.
Because
Except that J3 is 0, so yeah.
that's 0, so e to the 0 is 1,
Right.
So the identity operator acts on these singlet states. These are scalar fields. Right. Let's go to something more interesting. Let's let J equal the next value, 1/2. Then we have 1/2, 1/2, and we lower that, and we have 1/2 and minus 1/2. Okay, those are the basis states. Then any linear combination of those, that gives us a two-dimensional space, and we should get a two-dimensional representation of our J3 and J squared. Well, let's look at J3. Between all possible pairs, so 1/2, 1/2, 1/2, 1/2. That's going to be what? Well, it's going to pull out 1/2 H bar, and then if these are normalized states, just give 1. If we look at 1/2, 1/2, J3, 1/2 minus 1/2, that pulls out the minus 1/2 H, but then these two states are orthogonal, so I get 0.
Yeah. You meant H bar.
Yeah. If we look at minus 1/2 J3 and plus 1/2, we're going to get 0 again because these two states are orthogonal, and that's an eigenvalue. And finally, with the minus 1/2 J3, we're going to pull out minus H bar over 2, and then we get 1. So J3 is going to be H bar over 2 times a matrix of 1, 0, 0, minus 1. This is the familiar polymatrix. What do you suppose we get for J1 and J2 in this same basis?
The rest of the
It's going to
polymatrices
be the other two polymatrices. This is SU2. Right?
Okay.
So we found the SU2 representation that we've already studied. Cool.
So by the time we go to the 3 dimensions, we're going to get SO3.
What happens with J equals 1? Proof left to rear.
That's a good way to end the class. So that's a good way to end the class.
Yeah, but you can find a matrix representation, and now what is the dimension of the space? Right, the dimension of the space is 2J plus 1. That's the number of different M's for any particular J.
Yeah.
Right, where J equals 0, 1/2, 1, 3/2, and so on. Well, that's going to be, in general, K over 2. So for K equals 0, 1, 2, and so on. So 2J is going to give K plus 1, where, all right, that is equal to 1, 2, 3, 4, and so on. So we get the space of every integer dimension, 1 to infinity. So we have a matrix representation for these J's of any dimension we choose. Right? And that will correspond to a certain value of total angular momentum, J squared. Right? So the eigenvalue j that gives us the eigenvalue of j squared. Is an index to these different representations. Now, these come up in quantum mechanics where you add spins, right? Particles have a spin and a half, but if you have a multi-electron atom and those spins all line up, there are ways to add those spins to get higher values and bigger representations. For fundamental particles, we're interested in j equals 0, 1/2, or j equals 0, 1/2, 1, and 2. Those are the particles that we have seen, or assuming the graviton is spin 2. But this gives us a classification of all possible invariant states under the Poincare group. So now we know what kinds of particles to expect, and we can start constructing them one at a time. We're going to look at scalar fields. We're going to look at spin 1 fields. We're going to look at spin half fields. We're going to look at spin 1 fields, right? And spin half is going to be the Dirac equation. Klein-Gordon field is spin 0. The electromagnetic field is spin 1. And by the time we do all that, we'll be in a position to gauge it and look at the electroweak theory, QED. Not the electroweak, I'm sorry, to look at QED.
You're right.
So,
Yeah, the cow's out.
The cow's outside.
all right, good.
Oh,